Hello, everybody. Today I want to talk to you about the continuous about the stellar evolution. Now I will share my screen. Yeah. First about the Hertzsprung-Russell diagram. As you see from the bottom in this diagram, from the bottom up to up, the mass and temperature and luminosity increase. And you see, we call this sequence, we call this main sequence stars. It is main sequence. And this line, we call this line zero age main sequence stars. And we call this border terminal age main sequence. And you see most of the stars are in main sequence, as our sun, which is in G2 entire spectral type. It is in G2, it is in main sequence. And we have other stars like white dwarfs and supergiants, giants, cool but bright giants. For this diagram, we call it the Hertzsprung-Russell diagram. Here we have a spectral type from all that the stars in here are the most hottest stars. The hottest stars are in O type stars, and then we have B, A, F, G, K, M, that the temperature and luminosity in here, for example, for K and M stars, are lower. But for here, that this axis, y-axis, it is absolute magnitude, temperature from down to up increase. For example, stars in here, they are the hottest and the brightest and the most massive stars in here. Most of them are young stars. And you see, but for dwarf, for example, for white dwarf stars, the temperature is high, but the luminosity is low. But for example, giants, we have the temperature is low, but the brightness is high. For our sun, it is in G2 type of stars. We have it in main sequence. And you see here, for example, you see here some stars, but we don't see any stars here. And I will explain it about them later. Here you see the evolution and the process of living for stars. For the massive molecular cloud, you see here is the molecular cloud, and we have proton star. If it is more massive, we have a blue supergiant star, and then we have black hole. And it is in for here again, it is the time or age, we call it, and here is mass. If they are more massive, we have a more massive star, and the evolution process of their living is different from the stars which their molecular cloud is in lower mass process level. And also you see our sun-like star here for this proton star, and then we have it will be a red giant, and then nebula, planetary nebula, and then we have white dwarf or type A supernova. And how for example, someone can detect the star, for example. But if we want to detect the spectra of a planet, for example, then we have planet for star for our sun. From the temperature, for example, we have a star, our sun, and then Jupiter wants to pass the transit in front of the sun, and then we have our Earth. But we cannot detect the surface of the Jupiter. Why? Because for the spectra, because we have the spectra of sun, the star, and also we have the spectra of our Earth. So we should reduce the spectra of the sun and for the Earth atmosphere. Then we can have detect the spectra of the planet, for example, Jupiter. So it has a long process. It needs a lot of precise detector and data for data reduction in spectral type. Here you see the evolution of a single star. As you know, we have binary stars. We have, for example, 2, 3, or 4 stars, but here is the evolution of a single star. In here, we have a molecular cloud. If the molecular cloud is too massive, we have more than one star. But if it is less massive, we have one single star. And how this molecular cloud collapsed to have one, for example, single star, because maybe we have another star near here, and that star explode, for example, for super massive star. For example, we have an explosion in supernova. If we have an explosion in supernova, and then the jets of that star has some influence to this molecular cloud, and the density of this molecular cloud changes, and then we have some regions, and we can have a single star. Or if this molecular cloud, we have this molecular cloud, and then one star pass this molecular cloud, and then the density of this molecular cloud, the momentum of this molecular cloud changes, and then we can have one single star. So first we have a dark cloud, then we have for example, after the influence of jets of the supernova or passing the star, we have one molecular cloud that it has some momentum and rotation. Then you see that we have gravitational collapse. Then these four collapse to each other, and they have one dark region. And then we have in protostar, we have a disk of the star, which in this disk, which it may be the shell or the dust gas, so we call it disk. We need it for generate of the planets. So we have a disk here, and then we have the bipolar flow that we call it jets of this star, singular star, from the star to outside. Also, we have a gravitation of the go to this star. And then in the top T-Tauri star, that in this region we have that disk like this, But the difference from the Tahereh star and protostar is in Tahereh star, we do not have this dust and gas material around the disk of the single star. The difference is this. And also we do not have gravitation influence, just we have jets and disk of the single star. And then in pre-main sequence star in here, we have disk, and also you see we have some planets. So in here we do not have jets or gravitation or material dust gas. Around the disk we have a star and we have planets. And then for example we have some planets. For example, if the important is if we have, for example, Jupiter planet here, we cannot detect it. Why? Because of the temperature. As you know, we can detect the stars, exoplanet stars, or exoplanet planets, exoplanets in infrared. In infrared, because of the high temperature of Jupiter-like planets, we cannot detect it because the temperature is high, and if it transit in front of the star, we cannot detect it in infrared. So we cannot detect the Jupiter-like planets. And then in here, as you see, we have hydrogen burning. The color of the star changes from red into yellow. So we have hydrogen in the core of the star, and you see we do not have disk. We have orbits of the planets, and we have a star, single star. These evolution are from one single star. From binary stars, the story is different. And you know, about more than 50% of the stars are in binary stars. And we have binaries in globular cluster in old range of the stars, and also in young star clusters, which they are young, as you know, in open clusters. So we have different kind of binary stars in young and open, in young and old clusters. And the problem is when we have, for example, binary stars, we do not know that in, for example, in open clusters, which star is the main star and which star is the companion. And I can show you in here, for example, in O-type stars, for example, we have two stars in O-type stars. One is a star, the main star, and the other is the companion. After a while, one of them give its mass into another star, the companion, for example, and that star become bigger and bigger, and it may be after a while it explodes and it leaves the companion. And after a while, for example, for our sun-like stars, solar-like stars, maybe we see a star, but we do not see the other companion. Maybe that companion would be a white dwarf star, and we do not know where is that companion. So we cannot detect it, and we call that star a single star. But maybe it was not single, it was binary stars, but we didn't know where is that companion. And as you know, we have two type of stars population 1, that they are we have it in young star clusters, and population 2, which we have it in old type of star cluster. And here you see isochrons of stars. Isochron is this line, and you see these are related to metallicity. We have different isochrons which it's related to different kinds of metallicity. So for each metallicity, we have one isochron. As you see, we have different kind of isochrons, and you see, for example, here is 0 main sequence stars and the boundary, and here we have terminal age main sequence star boundary, and you see, as I told you, you see a gap here. We do not have a star here, but we see the isochron or the path of that stars here in the diagram. So what happened here that we call it Hertzsprung-Russell gap? We can say as a star, they live in main sequence stars. After a while, when they want to leave the main sequence, they have some process in here which it is too fast. When we call it fast, we do not mean, for example, 1 second. In astronomy, for example, in the process of the star evolution, a few million years is a few. It is fast. So they have some fast process here, and when they leave the main sequence, they do some process very fast. For example, shell burning. They do it too fast, and after a while they become, for example, supergiants. And there are some gaps here. And that's it for today. I hope it would be useful for you, and see you next time. Bye.